Hi students, so we will continue solving the problems, JE problems. Last time we did up to question number 29. Okay, so 30th question you see. So in question number 30, they are saying a heating coil is rated. So there is a coil, rating of a coil is given 100 watt, 20 to 20 volt. So I have told you numerous times, okay, the moment you are given the rating, power rating and voltage rating, the first thing you should calculate is the resistance of the coil. So resistance of the coil will be power voltage rating square by power rating. So voltage rating is 220 into 220 divided by 100. So this will be 484 ohms. So resistance of this coil is 484. Okay. So now what they are saying, the coil is cut in two halves and the two pieces are joined in parallel to the same source. To the same source means the voltage will be same. Source is same, so voltage will be same. So now when you cut the coil in two halves, you are cutting, remember, you are not stretching or you are not compressing. So when you cut, the area will remain constant. And you know resistance is inversely proportional to length. So when it is cut into two equal half, resistance of each coil or each part will be half of the initial resistance, right? So if the resistance is R, once you cut into two equal half, each part will have resistance R by 2 because resistance is inversely proportional to length. So this means the resistance of each part will be 242 ohms. Okay, so now these two parts are now connected in parallel. So imagine this original coil was this one. Then they are cutting this into two equal parts like this. Then they are joining these two in parallel. Okay, and connecting the same source. So if this has some resistance R, this will be R by 2, R by 2, which we have calculated 242. Then these two parts are connected in parallel to the what source? Same source. So since the voltage is the same, to find the power consumed now, they are asking what is the heat consumed per second. Per second means power only, right? Heat per second means power. So now the power consumed by this circuit will be R by 2 in parallel will be R by 4. So since I know the voltage, I will write voltage square by R equivalent, which will be voltage square by R equivalent will be this R by 2 is how much? 242. Here we have calculated, right? So 242 and this is also 242. So 242 ohm in parallel will give you 242 by 2, right? So R equivalent will be 242 by 2. Okay, which is actually this R divided by 4 also. Same thing. So voltage is same, they said the source remains the same. So 220 into 220 divided by this will be 121. So that will be the power consumed by the circuit which has these two parts in parallel. So first they had one coil, then they cut the coil in equal halves. So resistance of each part will be half of the original resistance. Then they are connecting those two in parallel. So resistance will become further halved. Okay. Then they are connecting the same source. So the power consumed now they are asking by the circuit, by these coils. So whenever there is more than one resistor, how to find the power consumed? If you know the voltage, write voltage square by R equivalent you have to use. Okay. So this will be 11 ones are 11 ones are 11 twos are 0, 11 ones are 11 twos are. So 400 watt is the answer. Here they are giving in the units of 10 to the power 2. So this will be 4 into 10 to the power 2 joules per second. Watt means joules per second. So this much joules is consumed per second. So answer will be option D, 4. Okay. So in question number 31, they are saying an electric tea kettle has two heating coils. Okay. When one of the coil is switched on, that means the other one is not used, only one coil is used, boiling begins in 6 minutes. Boiling of some water. When the other coil is switched on, boiling begins in 8 minutes. In what time will the boiling begin if both the coils are switched on simultaneously, first in series, then in parallel? So let me do it for first series. Okay. So first the problem is saying like this. First they have two coils in the kettle, but initially only one coil is used. Okay. So when first coil is used, boiling begins in what time they told? 6 minutes. So let us say it is T1. Okay. So what is the formula for how much heat you need to boil water? The amount of heat required to boil water is mass into specific heat into change in temperature. So this formula you know from first PU. So this is the amount of heat which is required. We used to write capital Q, right? Okay. So now the mass of the water is not mentioned. Specific heat of water is obviously constant. And you know for boiling the temperature should go up to 100 degrees Celsius in each case, right? So since mass is not mentioned, we will assume the mass for the water is constant in each case. So when the first coil is used, this much heat is provided through the power which is consumed through the electricity. And what is heat energy? Power into time, right? So power in the first case will be when only one coil was used. So let us say the resistance of that coil is R1. Also, we have to assume that the power supply, the voltage is constant. Obviously, right? If the kettle is used at home, whether you are using one coil or both the coils in series or the second coil, the voltage that is given to the kettle, that will be constant from the power supply. So we have to understand that voltage is same in this problem. So the power we can write V square by R1 into T1. Okay, so this is the heat which is needed to boil the water, which comes from the power consumed by the resistor. And when there is a voltage applied, the power consumed is voltage square by resistance, and time taken is T1. This is when the first coil is used. Now when second coil is used, it will have a different resistance, right? R2, let us say, is used. They said boiling begins at what time? T2 they told. Why T2? Because resistance is different for the second coil. Voltage given will be obviously constant. Same voltage you must be giving to the kettle. And heat required is also same because the mass of the water was not mentioned. So I'm assuming the mass of the water taken in the first case and in the second case is same. And for boiling, you know change in temperature should reach up to 100 degrees Celsius if you are starting from room temperature. So this is constant, this is constant. Then why you are taking different time? Because you are using a different coil. Okay, so when second coil is used, the heat developed is given by power into time. Power is what now? V square is same, but resistance is different, T2. Equation 2. So now they are asking how much time it will take. First, this time they have mentioned. In the first case, time taken was 6 minutes. And in the second case, time taken was 8 minutes. Okay, so now when they are used in series, what time it will take? So when it is used in series, both the coils. So when both the coils are used in series, again you are trying to boil the same amount of water only. So Q will be same, voltage still is same only, but now it will be R equivalent. R equivalent into some time in series, let us write TS. So this TS we have to find. Now you know this R equivalent in series is what? Let me write this formula here. Later we have to use Q equal to V square by R1 T1. Also Q equal to V square by R2 T2. Okay. So now when we are using in series, the two coils, this much is the equivalent resistance, right? So this I can write Q equal to V square by R1 plus R2 into Ts. So now how to find a relation between this Ts and this T1, T2. So look carefully what I can do. For R1, what I can write from here. Look the first equation. For R1, I can write V square by Q into T1 plus V square by Q, and for R2, I can write V square by Q into T2 times Ts, right? So you can see V square is common, it will cancel. This Q is common, it will go in the numerator. That Q will also cancel with this Q. So 1 will be equal to Ts divided by T1 plus T2. Therefore, Ts will be what? T1 plus T2. Okay, so in series, if they give, try to memorize this result. Try to memorize this result. Okay, so if the first coil takes time T1, second coil takes time T2, then when you put them in series, they take how much time? T1 plus T2. I have done the derivation. So for exam purpose, try to remember that. So directly you can substitute. First time was, I think, 8 minutes. First time was 8 minutes. Second time was 6 minutes. So it will be 14 minutes. Now when it is used in parallel, these two are obviously same. In parallel, here you have to write R equivalent, and that will be what? That R equivalent, you can write, here you can write 1 by R equivalent, you can write 1 by R1 plus 1 by R2. And that I want you to try. So if it was in parallel, if the two coils are used in parallel, okay, if the two coils are used, let me write here, in parallel, then the time taken, you try to do that, the time taken would be Tp, let us call it, that will come T1, T2 by T1 plus T2. It is expected also. For series, if you got this, for parallel, you should get this. For series, if you got this, for parallel, you should get this. Okay, so try this yourself. So what will be the answer? 8 into 6, 8 plus 6. So that will be 48 by, let me remove this part, 48 by 14. Right, 14, 2 7s are, 2 1, 2 2s are, 2 4s are, so 7 3s are 21. So 3 point something seconds. 3 point something seconds it will come. Okay, or minutes actually. So 3 point something minutes. So which would be the right option? 14 and 3.43. So option 1. Okay, option A. No need to calculate this. You can just check the option and tick the right one. Okay. 32 we have done already. Okay. 33 you see. So in question number 33 they are saying an electric bulb rated 500 watt and 100 volt. So rating of bulb is given 500 watt, comma 100 volt. So from here what you should quickly find resistance of the bulb. B I am using for bulb. So voltage square is 100, power is 500. Directly we can do, right? So that will be 20 ohm. So 20 ohm is the resistance of the bulb. Now they are asking, that means if you apply this much voltage, then it will consume this much power. Now they are asking, calculate the resistance R that must be put in series with the bulb so that the bulb glows with maximum brightness. Now, if you read again, an electric bulb rated this much is used in a circuit having 200 volt supply. So this bulb, whatever resistance RB it has, see, if you apply 100 volt, then it will consume 500 watt, but they are applying 200 volt. So if you apply directly 200 volt, this bulb will fuse because the rating is 500 watt at 100 volt. So if you apply 200 volt, that is double of this voltage, double of rated voltage, then power will be more than rated power, then the bulb will fuse. Okay, so what they are asking is how much resistance we should put in series so that this can glow with maximum brightness. Maximum brightness means it should glow with the rated power. So by putting this resistance in series, then we can make this bulb glow with maximum brightness instead of just getting fused. Directly 200 volt you should not apply here. So 200 volt. Okay. So since you want this to glow with maximum brightness, this should consume this much power. But to consume this much power, this much voltage should be applied here. That means out of 200, 100 should come here. Please understand that, okay? Because they said this should consume, this should glow with maximum brightness, means it should glow with this power, which means here the voltage must be 100. Now if here it is 100, here it will be also 100. So we already know the voltage for this resistor. To find this resistance, now I need to find somehow the current flowing in the circuit. Current flow. There's no point doing R equivalent because you don't know R itself, right? So what you can do, you know that this is consuming this power only. So in this problem, power consumed must be same as rated power. Why? Because they want the bulb to glow with maximum brightness. So power consumed is same as rated power in this problem. So 500. Now since I want the current, and you know current in series will be same everywhere, and here how much current is flowing? I. So I can write this power consumed I square into resistance of the bulb, because this is power consumed by bulb, equals to 500. And what is the resistance of the bulb? We calculated 20. So 500. So 0's cancels, 225 so current is 5 amperes. Okay, so once I know the current here is 5 amperes, I can now find the resistance of this resistor by just using Ohm's law for this. So voltage here should be 100, current here is 5 amperes, voltage by current is resistance, so that will be equal to 20 ohms. Okay. Okay, let us see question number 34. A cell develops the same power across two resistors R1, R2 separately, they are saying. The internal resistance of the cell. So this problem is based on mainly algebra only, okay? So what they are saying, there is a cell, first they are connecting it to R1, then they are connecting it to R2. The power consumed, the power across the two resistors, matlab power consumed by the two resistors are equal. So power consumed by the first one is same as power consumed by the second one. This is given to in the question. Now first resistance is, let us say, has value resistance, they have given capital R1. So I can write power as current in the first resistance square into resistance. Current square into resistance, right? This is the formula for power. Now current, how much is flowing? EMF of the cell divided by external resistance plus internal resistance square, R1. And current in the second case will be how much? EMF of the cell will be same, because same cell they are using, only the external resistance they have changed. So current will obviously change. So that's why I wrote current here I1, here I2. So EMF is same, external resistance is R2 in the second case, internal resistance also will be same. Many times I have told you EMF and internal resistance depend only on the cell. So this we have to simplify. So you can see E square will cancel. So it will be R1 divided by R1 plus R whole square should be equal to R2 divided by R2 plus R whole square. Okay, so this we have to just simplify. So let us try to simplify. Cross multiply R1 R2 square plus R square plus 2 R2R. Okay, A plus B whole square formula I have used. And here you cross multiply R2 will into R1 square plus R square plus 2 R1 into small r. Then multiply with R1. The first term will be R1 R2 square plus R1 R square plus 2 R1 R2 small r. Same thing you do here also. Okay. R2 R1 square plus R2 R square plus 2 R2 R1 R. Right? Okay. Then you can see this part and this part are same, so you can take it that side and cancel. Okay, then here I want, remember, small r. Okay, internal resistance they are asking. So let me bring r2 r1 square this side. So r1 r2 square minus r2 r1 square, and let us take this one that side. So r2 r square minus r1 r square. Here let me take r1 r2 common, so it will be r2 minus r1, and here let me take small r square common, r2 minus r1. Easily you can see r2 minus r1, r2 minus r1 will cancel. So therefore small r square will be equal to r1 r2. So small r will be square root of r1 r2. So this will be the internal resistance if the power consumed by the two resistors separately are equal. Okay, so you can check which option it is. Pause the video and write please. Okay, even NEET students should concentrate on all these questions because all these questions are very basic level. Okay, so you should be able to solve, and they can ask in NEET exams also. So let us see next question now. Question number 35. A given resistor cannot carry currents exceeding 20 ampere. So there is a resistor, maximum current should be 20 ampere. So if the current becomes more than 20 ampere, probably the heat produced will be so much that the wire will melt without exceeding its maximum power dissipation rating. So every coil will have some maximum power rating which it can develop. More than that it should not. So this is the current which will produce that much maximum power. So that is why this is the maximum current. More than this current should not flow. Now by forced air cooling, suppose that we increase the rate at which heat can be carried by a factor of 2. Now the maximum current that the resistor can carry is how much? Simple proportionality problem. So what they are doing, by using some cooling method, they are able to increase the rate at which heat is carried by a factor of 2. So by cooling the wire, they are making the wire consume more than before. Whatever was the power before, now it is able to consume more by a factor of 2. Rate at which heat can be carried. See, rate at which heat can be carried, matlab what? Heat per second. That means power consumed. So you are able to increase the power consumed now. Why? Because you are cooling the wire. Okay. So they are increasing power consumed by factor 2. So by what factor maximum current will increase? Simple, we know power maximum which is consumed should be proportional to I square maximum in this problem because current is mentioned. So if power increases by 2 times, current must increase root 2 times because there is a square here, right? The same thing I can write I max is proportional to root of power. So if power increases 2 times, current will increase root 2 times. Okay. So maximum current will now be root 2 times the old one. Old one was, let me write dash here. So old one was 20 ampere. So now it will be able to carry 20 root 2 amperes. Before it was 20, now it is increased to 20 root 2. Simple problem. It is just based on proportionality concept. Let's see the next question now. Question number 30, how much? 6. So in question number 36, they are asking, in the figure shows if a network of 3 resistances, when some potential difference, not same, some potential difference is applied across the network, the thermal powers dissipated by A, B and C are in what ratio? So let me draw the diagram first. So here is a resistor, here there is a resistor, and here there is a resistor. This is C which has resistance R, this is A which has resistance 3R, this is B which has resistance 6R. Okay, so we have to find the ratio of the powers consumed when some voltage is applied, some voltage which they have not mentioned. Now you know whatever voltage may be, some current will come, that current will divide here I1, I2, right? And then the total current will flow here. Yes or no? So power consumed by this C, we can directly write power consumed by C, I square R, right? Power consumed by C. We have to find power consumed by A in terms of this current. So how we will do? We will find I1 and I2 first using branch rule, which I taught you last class. So what will be I1? I1 will be resistance of the opposite branch, 6R, divided by sum of resistance, sum 3R plus 6R into main current. This is the main current. So this formula I've given, if you remember, use it. If you don't remember also, you know voltage here should be same. So from that concept also you can derive this, but better to memorize this result. So this will be 6 by 9, R will cancel, 6 by 9 I can write 2 by 3I. So current in this resistor, A resistor, is 2/3 of the main current. So power consumed by A will be how much? Current square into resistance of A. Okay, this is resistance of C, remember. So what is current in the resistor A? 2/3 of I, square it, 4 by 9I, and resistance of A is 3R. So this 3 and 9 you can cancel, so it will be 4 by 3, square I missed, 4 by 3 I square R. Okay, so this is the power of A in terms of I did. So that ratio when I calculate, no ratio, I square will cancel, R will cancel. So now let us find this I2. So to find I2, use the same technique, branch rule you apply. So I2 will be equal to resistance of the opposite branch, 3R, divided by sum of resistance, 9R, into main current. So that will be I by 3, right? I by 3. Let me just slightly, yeah, I by 3. So this current is I by 3. So power consumed by this third resistor will be how much? Current in the third resistor is this. This is power consumed by B. Sorry, second resistor. First resistor, second resistor, third resistor. So power consumed by B will be I2 square into resistance of this, which is 6R. I2 we know is I by 3. So I square by 9, 6R. So that will be 3 2s are 2. Let me write here 3 3s are. So that is the power consumed by bulb B. So now we know power consumed by each resistor, not bulb I think, in terms of same factors, I square R, I square R, I square R. So now we can easily find the ratio. So power consumed by A is to power consumed by B is to power consumed by C. What will be ratio? First is this A, this is 4 by 3. B is 2 by 3. And C is just 1, right? I square R, I square R, I square R will cancel. So you can multiply by 3, 4 is to 2 is to 3. So that would be the ratio. Which is the right option? 4 is to 2 is to 3. Option C. 37th question you see. So in question number 37, three 10 ohm, 2 watt resistors are connected as shown in the figure. 10 ohm, 2 watt. That is the rating. This time they have given you the resistance. One resistor here, one resistor here, one resistor here. Rating is 10 ohm, 2 watt. Okay, now they are asking the maximum possible voltage between A and B. So this is A, this is B. Maximum possible voltage between A and B without exceeding the power dissipation limits of any of the resistor. So none of the resistors should consume more than this power. That is what they are saying, because this is the rating of each resistor. So resistance will be same, we know, 10 ohm, 10 ohm, 10 ohm. But they are saying none of the resistor should consume more than this. Remember, this is the maximum power. So what possible maximum voltage can you apply here, they are asking. I can show here also, but let me show this side. So the maximum voltage that is possible between A and B. Okay, so question is clear, right? Okay. So now see here. If this is consuming maximum power, okay, so let us, what we will do, first let us convert this into equivalent resistance like this. This is A, this is B. Okay. So what would be the equivalent of 10 and 10? It would be 5 ohm in parallel, and this would be 10 ohm, right? Now in this series combination, no matter what, whatever current flows should be same, that we know. So if voltage here, let me use same color only. If voltage here is V1, voltage here is V2, there has to be some relation between them. In capacitors also we have done similar problem, if you remember. In capacitor also we calculated the maximum voltage that can be applied without any of the capacitor breaking down. Okay, similarly, what is the maximum voltage we can apply so that none of the resistors should fuse? When it will fuse? When the power consumed is more than 2 watt, remember. So first what I did, I found equivalent of these two so that it looks more simpler. Now you know that there has to be some definite relation between V1 and V2. Why? Because it is in series. In series, current must be same. So current here will be what? V1 by R. Current here will be what? V2 by R. Right? Current is voltage by resistance. So that means what is the relation? 5 2s are 10. So therefore V2 must be twice of V1. So voltage here must be twice of V1. Keep in mind. Now, if this is the power rating and this is the resistance, then we can find voltage rating. Voltage rating means the maximum voltage each one can uh, develop so that the power consumed is maximum. More than this voltage will result in more than this power. Then the bulb will fuse. So what is the power voltage rating? We know the formula P equal to V square by R. So V square will be root of power into resistance. This is power rating. Okay. So power rating in the problem was 2, resistance is 10. So root 20. So each one of them should not get more than root 20. Now look carefully. This is the relation between V1 and V2, which is voltage across this, or you can say voltage across these two also. Because in parallel, these two are in parallel. So voltage here, how much is, I have written V1. That will be here also, right? Okay. Now concentrate. Suppose I say V1 is root 20. Because maximum I want, no? So if you want maximum voltage here, these two, one of them should be maximum, right? So if this is maximum, sorry, if V1 I take maximum, V2 will become how much? 2 root 20. 2 root 20 means 10 ohm will get more than root 20, which means 10 ohm will fuse. So this we should not allow. This should not be allowed. So what we should do? This one I should make root 20. So if V2 is root 20, then V1 will be V2 by 2. So root 20 by 2. So if V2 is root 20, look here, if V2 is root 20, V1 will be root 20 by 2, which is less than root 20. So this is also safe, this is also safe. And this is working at the maximum. So that is the maximum possible voltage. So maximum possible voltage between A and B will be this V1 plus V2. And we have used here maximum. V2 we have given maximum. How much? Root 20. Then V1 will have a definite relation. You cannot make this also root 20, this also root 20. It is impossible because these two are in series. So in series, current must be same. Current must be same, matlab voltage by resistance here, voltage by resistance here must be same. So there will be a definite relation between the voltage. You cannot make both of them maximum. Okay. So one of them should be maximum, then you have to test. By putting this one root 20, you see this V2 will become more than root 20. then this resistor will fuse. They are saying maximum voltage that can be applied without any resistor consuming more than the rated power. So to consume the rated power, the rated voltage is root 20. This I have calculated separately. So this is the maximum voltage each one can develop, or each one can have across its terminals. Okay. So this is V2 is root 20. So V1 should be root 20 by 2. So then you can add, right? So if you add, how much will you get? This will be 3 root 20 divided by 2. 3 root 20 divided by 2. And root 20 I can write 4 into 5. So 2 root 5. 2 will cancel. So 3 root 5 volt. So that much maximum voltage can be applied across the combination. So answer is 3 root 5. Option 37. Okay. So please go through this problem once more. It is a good problem. It is similar to the one that we did in online class also while dealing with capacitors. So see next question, question number 38. The efficiency of a battery when delivering maximum power. So when delivering maximum power by a battery, what will be the efficiency of the battery? So for efficiency of battery, first definition you should know. So efficiency of a battery is efficiency of anything is output by input. So this output power by input power. So power, you know, we can write current into voltage. So since output power they are saying it is when the battery is used in a circuit, then in the output matlab in the resistor how much power will be produced? Current into voltage, terminal voltage, because the resistor will get this much voltage. And input power is the one that is given by the battery, that will be current into EMF. EMF is the potential difference between the terminals of the battery when the battery is not giving any current. So this much input power, this much power can be given by the battery, but we know because of the internal resistance this much will be only the voltage when you actually connect the battery to a circuit. So this would be the efficiency of a battery. So current would get cancelled, so it will be V divided by E. Now how can we find a relation? We know E, or we can write V is E minus I into R, because current is given by the battery. So in this case, while delivering maximum power, already I have discussed with you, while delivering maximum power, your resistance will be, your external resistance must be equal to what? Internal resistance. So that time current will be what? EMF divided by total resistance. Usually we write R plus small r. But while giving maximum power, this is the condition. So while giving maximum power, they want efficiency, right? So while giving maximum power, external resistance must be equal to internal resistance. This is a theorem also. It is called maximum power transfer theorem. In class we have discussed. So just put capital R equal to small r here. So you will get current will be equal to EMF divided by 2R. Then put this current back here. What will you get? Terminal voltage. EMF minus current is EMF by 2 small r into small r. Small r cancel. EMF minus EMF by 2 will be EMF by 2. So we know terminal voltage is EMF by 2. Put it back in the formula of efficiency of battery. So efficiency will be V is E by 2 divided by E. That will be 1 by 2, which is 50%. So please remember this. Again, try to memorize this result. So efficiency of a battery while giving maximum power is half. Half meaning 50%. Next question that we are going to discuss is very, very important. I may be discussing it in the JE level, but the same question has come in CET also. Okay, even in CET. So in many textbooks they are doing it directly by using a standard formula, but I want to tell you how that formula comes. But first let us read the question. A fuse with cross-sectional radius of 0.15 millimeter. So there is a fuse, matlab basically a wire which should have high melting point, so that it can stay without melting for long time. Matlab more current can flow without it getting too hot and melt. So you can't use a wire whose melting point is too less. Then you will pass less current also, it will become hot, little bit hot, and immediately it will melt. You don't want that. So fuse means basically wire only with some resistivity. So a fuse with a cross-sectional radius, matlab this radius here, this radius is of 0.15 millimeter, blows at 15 ampere. So when the current is 15 ampere, it blows, meaning 15 ampere is the maximum current that the wire can tolerate. What should be the radius of cross-section of a fuse of same material which will blow at 120 ampere? So if you want to make the limit of the current from how much to how much, from 15 ampere to 120 ampere, then what would be the radius of the wire required, they are asking. What would be the radius of the wire required? So to do this problem, which is question number 39, very important for all entrance exam, first understand that when there is a wire, it will be initially at room temperature. Then when current will flow, power will be consumed, heat will be developed, I square R. So that power consumed will make the wire hot. Matlab it will have some higher temperature than room temperature. So since it is at higher temperature than room temperature, according to your first PU concept, it will start radiating heat from its surface. Okay, it will start radiating heat. So when the power lost by radiation is equal to power consumed from electricity, when these two become equal, then the temperature will reach a steady value. So when the wire, which is fuse in this case, has a steady temperature, which let me say is T, then power consumed, which is I square R, must be equal to power lost by radiation, thermal radiation. Okay, so I square R into power lost by radiation. Now for that you have to go to first PU concept. You can use Newton's law of cooling, but then there no, you will not get the exact formula. So better to use Stephen's law. So according to Stephen's law, what is the power lost by a body when its temperature is more than surrounding temperature? Try to recollect the formula. The formula for power lost is emissivity, then surface area. Let me write S here. S means the surface area, because the wire, this area will be very small, so you can neglect this area when it comes to loss of power. So this area you can neglect. So the loss of power through radiation, thermal radiation, will happen from the surface. So this is the surface which is important, this part. So I am writing S, okay, into Stephen's constant T power 4 minus T naught power 4. T naught is the room temperature. Okay, so this formula you please see your first PU notes. You will find under the topic Stephen's law. So E into surface area, Stephen's constant, temperature which it has, minus surrounding temperature power 4. Okay, now look carefully one thing. The resistance will be what? Resistance of the wire will be what? Rho L by A. Now this A and this A are not same. This A is the surface area, curved surface area. This A, when we write for resistance, you already know, for resistance when we write A, it means this A. This A, right? And if the radius is R, what will be this A? Pi R square. Okay, so be careful. And the surface area, how I can write? If the length is L, the heat is lost from the surface. So how can I write curved surface area for a cylinder? 2 pi R into L. Correct or not? Stephen's constant temperature power 4 minus room temperature power 4. Now, if you want this temperature to be just the melting point when the wire will blow, then this current will be that time the what current? The maximum current. Yes or no? So when the current has reached the maximum, when the temperature has reached the melting point, this current also will be the maximum. After that, you don't want more current than this. If the current becomes more than this, then the temperature will become more than melting point. Then what will happen? The wire will blow. It will fuse. So this melting point for a given material is always constant. So they say the material remains the same. So temperature is constant, sigma is constant, pi is constant, L will cancel. So very interesting, it does not depend on the length. Resistivity also will be constant for same wire, for same material, sorry. So therefore, if you cross multiply R square, what do you see? The maximum current which can flow, the current square will be proportional to radius of this wire, cross-sectional radius cube. So this is the formula which many textbooks use directly. I am trying to derive it. Okay. So this you try to remember for your exam purpose. It is similar to your um, Kepler's third law, right? Similar to that, but it is not, obviously there is nothing gravitation going on here, right? Okay. So if you remember this formula, remember this I is the maximum current at which the wire will be about to melt. So this is also called the limiting current. So when you buy a fuse, that limiting current will be mentioned. Okay. So it is very clear that I1 by I2 square is equal to, because it is proportional, equal to R1 by R2 cube, which implies, and sometimes they may ask you just proportional. Your current is proportional to what power of radius? So that time you have to write R power 3 by 2. So this also they can ask. Okay, so here, what is the first current? First current is 15 ampere. Second current is 120 square. Radius of the first case is 0.15. Second is R2 cube. Right? This we have to simplify. So 5 3s are 5 2s are, then 2 carry, 5 4s are, 3 8s are, right? So this will be 1 by 8 square will be 1 by 64, 0.15 divided by R2 cube. So then you take 1 by 3 power, cube root you take. So 0.15 divided by R2 will be 1 by 6 power 1 by 3, cube root. So cube root of 64 is 4 only. So cross multiply. 4 5s are 20, 0 2 carry, 4 1s are 4, 6.0. So 0.6 millimeter. So that should be the radius of the second wire. Material is same. Okay, option C. So very good question, try to see it, okay, carefully once. By the way, diameter, if they are same thing, because radius is what? Radius is diameter by 2. So first diameter by 2, second diameter by 2. 2 will cancel. So the relation between current and diameter will be same as current and radius. Okay, so proportionality will be still true. I can still say current is proportional to diameter of the wire power 3 by 2. Okay, let us 40th question I have done in the last video, Thursday video class. So we will go for 41 now. So if you look at the question number 41, the diagram given is a Wheatstone bridge. So try to remember whatever has been discussed in Wheatstone bridge. So a battery of internal resistance 4 ohm is connected to a network of resistance as shown in the figure. In order that maximum power can be delivered to the network, the value of R should be how much? So let me show you the diagram first. So here is a resistor 6R, here is R, here is R, here is 4R, then here is R, here is also R, and here is also R. Okay, and battery is connected here like this. Fine. So you can clearly see it is a Wheatstone bridge network. So if you slightly turn this side, you can see these two are in series, and you can see these two are also in series, because between these two there is no junction. Between these two, sorry, not these two, there is no junction, right? So R and R in series you can replace by 2R. So you can rub this one, and you can just put one single resistance 2R. Similarly here R and R is in series, so you can replace this by 2R. So now if you look the diagram, this is like, this circuit, P here, Q here, R here, S. So this is like your P, Q, R, S. Okay, let me put circle. So I'm writing this so that you can compare it with Wheatstone bridge. Okay, so you can see in Wheatstone bridge also we have like that, no? One here, one here, one here, one here. In the middle there is a galvanometer whose resistance is 6R. And across the opposite terminal there is a battery. Not here, okay, here. Opposite terminal. So I hope everybody has realized that this is like a Wheatstone bridge. Okay. So now we have to check whether it is balanced or not. So P by Q is how much? Check. R by 2R, which is half. And R by S. R by S is, R is 2R and S is 4R. So that is also 1 by 2. So it is a balanced Wheatstone bridge circuit. So since it is balanced, meaning this can be removed. So if you remove this, you will get like this, right? So finally it will be like there is a battery here, and these two are in series, so that will be 3R, right? These two can be replaced by one resistor, and these two are also in series. So this one can be removed, and here you have 2R, and here you have, let me draw it properly. So here, let me do it here only, okay? It will be easier to understand also. So R and 2 are in series, so you can replace it by 3R. Here you can put 3R. And 2R and 4R is in series, so you can write here 6R. And you can see between these 2 points, these two are in parallel because these two are joined directly, these two are joined directly. So these two are in parallel. So what will be the total external resistance? Total external resistance. 3R and 6R in parallel will be 3R into 6R by 3R plus 6R, 9R. Sorry. This R will cancel with this R. 3 2s are, 3 3s are, 3 3 cancel. So 2R. So external resistance of the whole circuit we have found. Equivalent external resistance is 2R total. So now they want power consumed to be maximum. Power consumed by circuit, they want this power to be maximum. And already we know from maximum power theorem, if power consumed should be maximum, external resistance, total external should be equal to internal resistance, always. So what is the external resistance? 2R. Internal resistance, how much they told for this battery? 4 ohm. So R should be 2 ohm. So which is the right answer? Option B. Okay, so simple question. Just you can compare it with first Wheatstone bridge, and whenever you hear current through a, power given to a circuit should be maximum, then it means external resistance of the circuit must be equal to internal resistance of the cell. Let us see question number 42 now. So in question number 42, they are saying Find the minimum number of cells required to produce a maximum current of 1.5 ampere through a resistance of 30 ohm, given that EMF of each cell is 1.5 volt and internal resistance is 1 ohm. So external resistance is 30 ohm and EMF of each cell. So imagine you have one cell whose EMF is given 1.5 volt and internal resistance is given 1 ohm. They want the maximum current to be 1.5 ampere in a external resistance 30 ohm. Okay, so we have to find the minimum number of cells. Okay, minimum number of cells. Minimum number of cells. Again, this is also a very common question. So how are we going to do this? Think about this. See, direct, you cannot put just one cell. If you put one cell, if you check the formula, it will not come. This much current will not flow in this resistor if you put only one cell. So you have to find how many cells you have to put. So for that, what we will assume is we'll assume there are n cells in series, n cells in series, and there are such m times m rows. Okay, like this you have to imagine. So this is the combination of cells you have to imagine. Okay, so this many cells you have to imagine, which will, if you connect to an external circuit which resistance is capital R, the current here should be 1.5 ampere. That is what they are asking. So how many cells we have to use? So let us try to solve. First, what we can do, what is the equivalent EMF? Equivalent EMF. Here it will be E. So in one row it will be NE in series. No, N times. So this will be having equivalent EMF NE. NE in parallel will be NE only. So equivalent EMF is NE. Okay. What about equivalent internal resistance? Small r, small r, small r. See, each battery has internal resistance, or each cell has internal resistance. So R, N times will be NR. NR, M times in parallel will be NR by M. This we have discussed in our online class also. So this is the equivalent EMF and the equivalent internal resistance. So the current going in this resistor, once you replace this by one cell, one battery, whose equivalent EMF is this much, equivalent internal resistance is this much, then current flowing in the external circuit, I can write E equivalent by R external plus equivalent internal resistance, right? So let me rub the diagram now. So the diagram was just to understand how I got these things. Okay, so let us calculate. Now they want the current to be maximum, which means your R external should be equal to R equivalent. Remember, okay, for current to be maximum, power developed will be maximum. And if power developed in the capital R resistor, in the external resistance, if the power consumed is maximum, then external resistance must always be equal to internal resistance. If there is only one cell and one external resistance, doesn't matter. Capital R equal to small r. But if there are many external resistors, like in the previous question, then we have to find equivalent external resistance. Previous question there was many external resistors. Here there is only one external resistor, but many internal resistors. So we have to find equivalent internal resistance. So that should be equal for current to be maximum. Now what is R external? 30. And R equivalent is NR by M. R is 1 ohm. So 30 equals to N into 1 by M. Okay, so from here I will get N equals to 30 M. So at least I have found a relation between number of cells in each series, each row, and this is number of rows. Okay. Now I need one more relation to find N and M. That will come from here. Let me rub this part. Yeah, this also I can rub. This you remember. Okay. So now current is flowing how much? 1.5. This formula let me write here. And equivalent EMF is NE. E is 1.5 divided by R external is 30 and R equivalent is NR by M. Yes or no? So 1.5 cancel, cross multiply. 30 and small r is 1, remember. So 30 plus N by M, because small r is 1 ohm. So just put 1 here, will be equal to N, right? So now you can just put directly here. See, N by M is how much from here? N by M is 30. So put directly N by M is 30. So 30 plus 30 will be equal to N. So N will be 60. So if N is 60, what will be M? Put 60 here. So M will be 60 divided by 30. That will be 2. So I got N equal to 60, M equal to 20. So number of cells used. Number of cells will be equal to N into M. Yes or no? Because there are N cells in each row. And how many rows are there? M rows are there. Okay, so N into M will be the number of cells. So N is 60, M is 2. So that will be 120 cells. So answer will be 120 cells. Okay. So that means minimum number of cells you need. Option D. 43, let us do. So please try to remember, if the current in the external circuit should be maximum, then external resistance must be equal to internal resistance. Question number 43 now. Under what condition the current passing through the resistance capital R can be increased by short circuiting the battery of EMF E2? The internal resistance of the two batteries are R1 and R2. So initially you have a battery like this, two batteries are there, and there is an external resistance E1 R1, E2 R2. External resistance is capital R. So under what condition the current through this resistance here can be increased, they are saying, by short circuiting the battery of EMF E2. Short circuiting means just putting a wire like this. Okay, just putting a wire like this. That is called short circuiting. So short circuiting means if you have something here, it could be a resistor or it could be a battery. If somebody says short circuit this resistor, short circuit it without any resistance being told, directly if they say short circuit it, then it means just put a wire like this or just put a wire like this. So by short circuiting this battery, under what condition the current can be increased, they are asking. So first let us see what is the current here. So current here right now, let us say is I. That will be, what is the equivalent EMF? E1 plus E2, because both of them are sending current in the same direction. So equivalent EMF is E1 plus E2, series combination, and total resistance is R plus R1 plus R2, right? Total resistance. So this is the current. Now if you short circuit the second battery like this, if you short circuit, then this will be useless now. Why it will be useless? Look here. So now the current coming from here, from this E1, that will flow like this, it will go like this, and then when it reaches here, it will go this way only. Okay, it will not go here. So this battery, this part will be useless once you short circuit whether a resistor or a capacitor or a battery. If you short circuit, that part will be useless in the circuit. So now the current will flow like this. So what will be the current? I dash, let me write. So that current, let me write I dash. So what will be I dash now? So now the battery which is sending the current is this battery. This is useless. So E1 by total resistance will be capital R plus R1. So this part will be useless, okay, because this is zero resistance path. So if this is zero resistance path, current, all the current will go here only, no? Why it will go in that branch where there is some resistance, okay? So they want how current can be increased. So they want this to be greater than this, okay? So let me rub this part. So now diagrams I think we don't need. So once we have understood this, they want this current should be greater than this. So E1 by R plus small r1 should be greater than E1 plus E2 divided by R plus R1 plus R2. And this we have to try to simplify. So the condition looks like, many things are there. So if I cross multiply, let me see what I'll get. E1 capital R plus E1 R1 plus E1 R2 should be greater than cross multiply. E1 plus E2 R plus R1. Okay. So let me further open this. E1R plus E1R1 plus E1R2 should be greater than E1R plus E1R1 plus E2R plus E2R1. So E1R, E1R I can cancel. E1R1, E1R1 I can cancel. So basically this should be greater than this. So let us see which option is this. E1 R2 should be greater than E2 common R plus R1. Yeah, second option. So E1 R2 should be greater than E2 common R plus R1. So option B. Okay, so this is more like algebra you have to do. That's it. So question number 44. This question I feel like I have done. Yeah, I have done it. Okay. So to find the energy stored in the capacitor, this we have done. In steady state we have done. But I would like to just revise it once. If you feel like we have done it, you can skip. Just fast forward and go to the next question. But let me try to revise this question because it is quite important. So see the question. A capacitor of 4 microfarad is connected as shown in the circuit. So there is a capacitor 4 microfarad is connected as shown in the circuit. So here 10 ohm. Here there is a battery 2.5 volt, and here there is another resistance 2 ohm. Internal resistance is also mentioned 0.5 ohm. They want the energy stored in the capacitor in steady state. So in steady state. So many times I have told, when they give you capacitor in a circuit with battery and all, and if they say steady state, then it means the capacitor has been fully charged. So plus Q minus Q, it has been fully charged and there is no current in this branch. So steady state means no current in the branch with capacitor. So this branch cannot have current once it has been fully charged. That means current will flow only here in steady state, okay? Not the state when it is getting charged. That we will study in Monday class. Monday, this coming Monday. So current will flow like this only. So let us find the current. Because they want energy stored. So we need to find the voltage here. Voltage. That's it. So first let us find the current here. So the current here will be EMF is 2.5 external resistance is 2, internal resistance is 0.5. Here no current is flowing, so this resistance we don't have to use it because no current is flowing there. So this will be 2.5 divided by 2.5, 1 ampere. So we know 1 ampere current is flowing. So we can ask what is the voltage here. So voltage here will be I into this 2 ohm according to Ohm's law, I into R. So current is 1, R is 2, so 2 volt. So we know voltage here is 2 volt. That means voltage here also should be 2 volt because these points are same common point and these points are common point. So here potential difference is 2 volt. So here also potential difference is 2 volt. But in this branch there is no current. That means no voltage will be here. That means the whole voltage will be here. Right? Usually we write this 2 volt will divide here and divide here. But here there is no current because steady state they told. So no current here means all that voltage will be only here. So once I know the voltage for this capacitor, what is the energy stored? Half CV square. Half C is how much? 4 microfarad, 10 power minus 6. Voltage here is 2 volt. So 2 square. So 1, 2 you can cancel. 8, 10 power minus 6 joules. Matlab micro joules. Okay, now you can find charge also. Charge will be how much here? C into V. C you know, V you know. So the main thing here is whatever voltage here you have calculated, same voltage will be here and therefore same voltage will be here because no current is in this resistor. You can find terminal voltage also if you want, same answer you will get. Okay. So if I have done this, you may have revised. Otherwise, please try to see this question again, very important question. Okay, let's see the next question now. Question number 45. So in question number 45, they are saying 4 cells of identical EMF E and internal resistance small r are connected in series to a variable resistor. So 4 identical cells are in series, are connected to a variable resistor. So this capital R is variable. So when I put arrow mark, it means it is variable. The following graphs shows the variation of terminal voltage. So whatever is the voltage here, terminal voltage, that voltage, they are plotting a graph of the voltage versus current. For what current does maximum power dissipation occurs in the circuit? So maximum power dissipation occurs in the circuit they are asking. For what current? So you know the graph is given like this. So try to look these coordinates, this point. So this point is, if you look carefully, 5.6 volt. This is volt, no? And this point, if you look carefully, is 2 amperes. Okay. Now, what will be the terminal voltage here? E equivalent minus I into R equivalent. Yes or no? We write, how do we write V formula? E minus IR for one cell. So you replace these 4 cells by one cell and write the terminal voltage for that cell. Understood or not? Okay. Current will be I because it is series. Everywhere same current. Okay. Now what will be equivalent EMF? 4E. Why 4E? Because each of them are identical and it is in series. And R equivalent will be 4R. Okay. So this is the relation between terminal voltage, EMF of each cell and internal resistance small r of each cell. Okay. So from here we have to calculate the current when the power dissipation is maximum. So let us try to first find internal resistance. Okay, so we know when external resistance equals equivalent internal resistance because more than one cell is there. That time power dissipation in the circuit is maximum. So look at this point. At this point, what is the current? Current is 0, right? Or at this point, voltage is 0. So voltage is 0 when current is 2 ampere. So from this graph you can see when current is 2 ampere, voltage is 0. Okay, and so let us substitute this condition here. So V is 0, 4E minus 2, 4R, right? So that means your 4E will be equal to 8R. So E will be 2R, equation 1, let us call it. Also look at this point. Here what is 0? Current is 0. Yes or no? So again use condition for this also. I think this we don't need now. So for this point, I can write when voltage is 5.6 volt, current is 0. So put this condition here. What will you get? When V is 5.6, 4E, current is 0 means this term will be 0. That means 4E will be 5.6, right? So this graph also is, the job of this graph is done. So from the graph, basically we have to just concentrate on those 2 points and use the condition for those 2 points in this equation. So from here we can find E and put it here. So from equation 1, E will be how much from here? 5.6 divided by 4 equals to 2R. So R will be 5.6 divided by 8, right? So this will be 4 2s are, 4 1s are, 4 4s are, 2 7s are, right? 0.7. So internal resistance is 0.7 ohm. Now when power should be maximum, external resistance should be equal to equivalent internal resistance. So external resistance should be how much that time? Equivalent internal resistance is not small r, it is 4R. 4R. R we found 0.7. So this will be 2.8 ohm. So once we know the external resistance, when the power is maximum, we can now find the current. So what is the formula for current? Current is E, since more than one cell is there, E equivalent, R equivalent, external R is only 1, internal there is more than 1, so I wrote R equivalent, small r equivalent. Now E equivalent, this is your E equivalent, right? So E equivalent, directly I can write 5.6. And when it will be maximum, when R is same as R equivalent, so I can write directly 2R. So 5.6 divided by 2R means just 2 times this, that will be 5.6 only. Just put the value of capital R here, that will be 1 ampere. Why 2R? Because R equivalent should be equal to capital R when power is maximum. So the current flowing that time is 1 ampere. Option A. Okay. So try to again see once how I have done it. So in this problem, four cells were given. If one cell is given, how will you do? See, the point is what? Here is your cell with internal resistance. Here is your external resistance. Okay, now if more cells are given, more than one, you will use equivalent, no problem. So this has equivalent EMF E, internal resistance R. This is external resistance capital R. You know formula for V is what? E minus IR, which means if this V is along y-axis, and then current is along x-axis, and this looks like what equation? Y equal to minus mx plus c. So it will be a straight line with negative slope like this, right? Yes or no? And here, whatever is the value of this, if the value of this is 5.6, then at that point, what is current? Current is 0. So when current is 0, V will be E. So this is nothing but E. And this will be your, when V is 0. If V is 0, what will be I from here? If V is 0, I will be how much? E by R. So this will be your E by R, this point. And if that point is given as, let's say in this question it was 2, then 2 like that. So what you can do is, if there is more than one cell, then this point, whatever number is there, no, that will be your E equivalent. And this number will be E equivalent divided by small r equivalent if it is more than one cell. Understood? So from here E we know, and from here E by R we know. So 5.6 divided by small r will be 2. So small r will be 2 2s are 4, 2 8s are 16. So 2.8 ohm. Right? So now if they want current here, how much it will be? E by R plus R. And when power is maximum, we know capital R and small r are equal. External resistance and internal resistance should be equal. So I can now write current as directly E by 2R. So E is 5.6, 2 into small r is 2.8. So 1 ampere. So it means what we have done here is, it means if you have more cells also in series, as long as they are identical, same answer you will get. So try to do the previous question this way also. How I did the previous question, I wrote the equation and then I wrote the condition. Right? I wrote at this point V is 0, I is whatever they have given. So that condition I used here. Then I used this point condition I used here. For this point V is 5.6, current is 0, right? So if there is more than one cell, what you have to do, just put here E equivalent, R equivalent. That's it. Okay. So power is maximum when current is 1 ampere, means here. That means somewhere at this point. So somewhere at this point your power will be maximum.